let's go ahead and do one of these electron configurations. Let's do arsenic. So this is AS, and this is element number 33. Okay, we have already done this in class. I just want to show you another time how to do it. So we're going to start out working with our periodic tables. Remember, we have the S block, we have the D block, the P block, and the F block. For this one, we are going to use the S, P, and D. So we'll start out with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, hope you can see these, 3d10, and then we're going to go to 4p, 1, 2, 3, 4p3. Okay, so there's your electron configuration. If we're going to abbreviate this from the skills we should have from this unit, hopefully, we will go backwards. And what I mean by backwards is we will go arsenic, we will go backwards to argon, and we will just write it out as, in brackets, argon. And argon gets rid of everything all the way up to 3p6. So everything after 3p6 is there. So you'd have 4s2, 3d10, and 4p3. Now you should also understand that we can get the electron, the valence electrons. The highest energy level we have is 4. So we're going to look at the fourth energy level. We have 2 there. We have 3 here. So we should have 5 valence electrons. Okay. Now, if you remember Aufbau's principle, it tells us that the first level is occupied first. So that just means we have the first one is occupied. Pauli's principle means that each orbital holds 2 valence electrons. Okay. So for 1s2, we would have 1 orbital. 2s2 would have 1. 2p6 would have 3. 3s2 would have 1. 3p6 would have 1, 2, 3. 4s2 would have 1. 3d10, oh gosh, 1, 2, 3, 4, 5. And then 4p3 would have 3. Okay, now all these are going to be full. We know that Hund's principle tells me you go the first one first in order. So it'd be up, down, that one's full. Up, down, full. We know these are full. This one's full. This one's full. This one's full. Now, when we get all the way, these are all full. But Hund's principle tells me I have 3, so I'm going to go up, up, up. Okay. And now the place we know if we become an ion and we're trying to become a noble gas, and we're probably going to add 3 electrons to this to make that happen, we have a spot form right there. Okay. So hopefully that makes sense. And that tells you Aufbau, Pauli, and Hund's rule. So you know how to get through the whole thing. You can find valence electrons. You can do all of the things. If you have an ion, you know where it goes. Now remember, you add, if you get a negative ion, you add to the place where it comes from right here because you have space for it. If it is a positive ion and you take away electrons, from the highest energy level. So that would be right here. If you say you had +2, you would take 2 away from here. Okay, hope that helps. So we had a question about number 20. Explain what happens when an electron gains and loses energy, and how does that correspond to a color? Show us a diagram. Well, here's your diagram. We're going to start out with 1, 2, 3, 4 energy levels for this example, and we know that we have an electron right here in a grounded state. Okay, it's at the lowest energy level, closest, and we'll say this is just the nucleus, closest to the nucleus. Now, what happens as this electron gains energy, it is going to jump quanta. Remember, quanta means we jump 1 level every time. And we'll say this one makes it to the outermost energy level, which is the 4th energy level. Now, once we're at the 4th energy level, what's going to happen is it's gained energy. It is going to emit this energy in the form of a photon. Okay, when the photon comes away, the color of that thing is going to correspond with how far this electron has to travel to get back to the center or the ground state. So the distance from the excited state to the ground state corresponds with the color, and that's what we saw in our flame test, where the different colors come from how far that excited electron can move. If it's a big element, it means that the inner levels are full, we'll say, and the electron can't move as much distance. That means it's going to be a different kind of color. If it is which will be a short distance, if it's a small element, the small nucleus, you'll have the innermost shell that's full, but it can move a lot more and can move a further distance. So the size of the element does dictate what color you can have. So questions number 14, 15, and 16. 14 says, what has a greater atomic radius, oxygen or fluorine? So we have oxygen right here, and we have fluorine right here. What we have to know is the atomic radius is related to a lot of things. And as we move in this direction, okay, we're going to figure out that there's more protons and there's more electrons. So the positive in the middle and the negative on the outside are going to be more attracted to each other. So this condenses and makes the atomic radius smaller. Okay. Now what that means is that also changes the ionization energy. Okay. The ionization energy, it also increases as it goes this way because of the decrease in size. The closer those things are together, the harder it's going to be for those things to get away, correct? So the ionization energy and the electronegativity, the closer the electron is to the nucleus, the more electronegativity it has, okay? So what we're finding out is as we go this way, the atoms get closer together, they get smaller, the radius gets smaller. As we go this way, they get larger. The number 15, the ionization energy, lithium or boron, okay, it's going to be boron is going to be greater because as we move this way, the energy to remove the outer electrons are getting more and more because they're closer together. And as we go this way, it's going to decrease because what we notice is the more shells we have, the farther we are from the center, the less energy it takes to remove one of those things, okay? Electronegativity works kind of the same way. The closer you are to the nucleus, the more electronegativity you have. So over here, the electronegativity is much greater than on this side, and it goes down as you go this way. Okay, so just make sure you know those trends and which way they go. It all has to do with the nucleus, the number of protons, the number of electrons, how much it's condensing the atom, and all the things that go with it. Hope that helps. All right, guys, last question, number 13. What is so special about group number 18? And please talk about valence electrons. Do they want to bond? Why or why not? That's kind of the question. The answer is no, they don't want to bond at all because they have a full outer shell of valence electrons. And we know that the ionization energy to remove one of those is really, really high. If we go to the other side of the table for something like sodium, we have one valence electron. And let's just say it takes X amount of energy to remove that one valence electron. Once you remove that and it goes somewhere else and bonds, does something else, once you remove it, the next shell is full, like a noble gas, like elements in group number 18. Now, the ionization energy to remove the next electron from sodium, which would be from a full outer shell, is 10 times X. So the energy goes up, way, way up. So it's hard to bond. They don't want to bond. Group 18 are noble gases. 8 valence electrons are a full outer shell of electrons. They don't want to do nothing. They are noble. Kings and queens, all of them.